Lecture 1A, Mathematics, Part 2. Continuing to learn our mathematical toolbox for the first unit of this course. The metric system of standard units are meters as our measure of length, kilograms as our measure of mass, and seconds as a measure of time. I refer to the system of meters, kilograms, and seconds as the MKS system. It turns out that any unit, standard unit that we'll use in this course, such as velocity and acceleration, can be shown to be based on 1, 2, or 3 of these units, such as velocity is meters per second. Acceleration is meters per second squared, or per second per second. Dimensional analysis is how we can convert from one form of units to another, such as from feet to meters. So let's convert 6 feet to meters using the technique of dimensional analysis. So I want to go from 6 feet to a number x of meters. Well, we'll use this fact that 2.54 centimeters are an inch. You can confirm this by looking at a ruler that has both inches, that measures both inches and centimeters. Well, the idea is to go from 6 feet using our factor 2.54 centimeters per inch. We know there's 12 inches in a foot, 2.54 centimeters in an inch. Crossing out the units, we see we're ending up with crossing out the feet, crossing out inches, crossing out centimeters. We're left with just the multiplication of 6 times 12 times 2.54 divided by 100. Pulling out of the calculator, we see that gives us the number of 1.83 meters. So we're down to just the unit we wanted, meters, after all the other units have been crossed out. So a 6-footer is 1.83 meters. But we just said 6, one significant digit. We didn't say 6.0, which may be an odd way of expressing in feet. We didn't say how precise we were, whether somebody is 5'10 or 6'2, and we just rounded and saying 6 feet. So with one significant digit, it's really best to say 6 feet is about 2 meters. That's the level of precision we're going for. Maybe it's a little bit more useful to say, just 2 significant digits, a 6-footer is about 1.8 meters. 2 meters would be more like a 6-footer with his hand stretched above his head, from foot to his outstretched hand raised above his head. That's about 2 meters. When you do your homework problems, you should have a ballpark estimate of where your answers should go. So if somebody drops something from hand height, you should expect the distance to be about 2 meters if you have to calculate that. If you end up with calculations showing it to be 200 meters or 20 centimeters, if when dropping something from a height from a hand held high, you would know you're not in the right ballpark. Part of learning how to convert from feet to meters is to go from a base that you're familiar with, feet, to something that you may be unfamiliar with, meters. Next, let's go from pounds to kilograms. So we went from an average person's height, roughly 6 feet, an average person's weight, roughly 150 pounds, and see what that person would be in our metric system in kilograms. Well, if we put a kilogram on a scale that measures pounds, 1 kilogram would equal 2.2 pounds. So we can use this fact to go from 150 pounds, cross out pounds, and end up with a number in kilograms. So 150 pounds is about 68 kilograms. But we're just going for a rough estimate. 150 pounds is about 70 kilograms. So the average person's weight is somewhere around 70 kilograms, roughly between 50 and 100 kilograms. Again, if you have a homework problem and ask for the weight of something that's about a person or a couple of people or something to be similar to that, you'd expect the answer to be somewhere between 50 and 100 kilograms. You've got an answer in tens of thousands of kilograms, or 1 kilogram or a tenth of a kilogram, it's supposed to be relating to something that's some other person's weight, you know that your answer is not correct. Next, let's go from miles per hour to kilometers per hour. Now granted, many people listening to this may be from international students, may already be familiar with the metric system, with kilograms and pounds, with kilograms and meters and kilometers per hour. But let's see, looking at our speedometer here, we want to make a conversion from miles per hour to kilometers per hour. And let's look at the speed limit. It says 65 miles per hour. That's a highway speed. So what is a highway speed expressed in kilometers per hour? Looking at the speedometer, where I circled it just now, you can see that 100 miles per hour is the same as 161 kilometers per hour. So 108 miles per hour mph is equal to 161 kilometers per hour. Well, 100 miles per hour is not a highway speed, at least not for me. But what would that be, 65 miles per hour being kilometers per hour? Well, let's use this fact and divide by 100. 1.61 kilometers per hour divided by 1 mile per hour. Well, they both have per hours on it, so let's cross all those per hours and go with 1 mile is equal to 1.61 kilometers. So now 65 miles per hour, which is mph. How many kilometers per hour is that? Well, divide miles out. 1.61 kilometers times 65 miles, and the miles cancel. And we're left with a number where the units are kilometers per hour. Plug this into our calculators. We got 105 kilometers per hour. Again, we're just going for a ballpark estimate. And we have 65, so we only have 2 significant digits. So it's best to probably write 100 kilometers per hour. So a highway speed is about 100 kilometers per hour. 100 kilometers per hour is a highway speed. So if you're doing a problem where, say, you're given a distance and an acceleration from a fast-moving car, and it stops and you have to figure out its original speed, or you have an acceleration over some distance and it reaches a highway speed, well, your units are going to be in the MKS system, and you'd expect the answer to be something around the 100 kilometers per hour. If your answer ended up being only 1 or a tenth or thousands of kilometers per hour, well, then you'd know that your answer is not correct, because a highway speed is about 100 kilometers per hour. 100 kilometers per hour sounds very fast. It's not the speed of a rocket. 100 kilometers per hour is simply highway speeds. So now you have a feel for the metric system, the MKS system, which helps you expect answers, ballparks the value of answers in your homework. Another dimensional analysis example. Let's go from 1 year. How many seconds are in a year? So we're going to go from years to seconds. Well, 1 year, that's 365 days. Now again, we're just estimating. I don't want to go through 65.24 or even more precise than that. We're just trying to figure out a ballpark estimate how many seconds there are per year. So in a day there's 24 hours, in an hour there's 60 minutes, in a minute there are 60 seconds. Cross out the units, and we're left with the proper units of just seconds. And this equals 3.15 times 10 to the 7th seconds. What is 10 to the 7th? 10 to the 6th is a million. 10 to the 7th is 10 with 7 zeros. 1 with 7 zeros, which is 10 million. So this is 3.15 times 10 million, or 31.5 million seconds every year. Well, 3.15 is a number that's similar to the first 3 digits of pi. It's not the same, but it's similar. So we can express 3.15 as the same thing as pi times 10 to the 7th. It's not pi, I realize that. But memorizing 3.15 times 10 to the 7th seconds per year is a bit difficult. It's a bit easier if we said pi times 10 million seconds per year. Again, there's nothing magical saying there are not pi seconds in a year. This is not numerology. We're just estimating. And so it's easy to memorize that there's about pi 10 millions, or pi times 10 to the 7th seconds in a year. Now, if we have a problem, and you'll have a couple that are similar to this one, how many heartbeats in a lifetime? Well, first we've got to think about how to estimate this. Do we just wait a whole lifetime and count heartbeats? Or is there an easier way to approach this example that we can start using our techniques of dimensional analysis? Well, we know that we have some ideas of the rate of heartbeats. When you get your heartbeat measured, it usually says something like your heart beats 70 times a minute, or 80 beats per minute. Or maybe it's a pretty healthy heart and it's 60 beats, or something a little bit less than that, or an unhealthy heart. You eat too much fast food and your heart beats are maybe up to 100 beats per minute. Well, we're somewhere between 50 and 100. We also know there's 60 seconds in a minute. So our heartbeats are not that different from how many seconds there are in a minute. There's about 70 or so heartbeats in a minute, and there's 60 or so seconds in a minute. So there's very roughly the same amount of heartbeats in a minute as there are seconds. So we'll say approximately 1 heartbeat per second. Again, we're just estimating. A lifetime, is it 60 years, 70 years, 81.23 years, 90 years, 100 years? Again, just estimate, let's go on the positive side, 80 years. So in 80 years, considering there's pi times 10 to the 7th seconds in a year, and there's 1 heartbeat about every second, then we're left with the proper units of heartbeats per lifetime. And that gives us, multiplying these numbers out, 3 times 10 to the 9th heartbeats per lifetime. What's 10 to the 9th? 10 to the 9th is 1 with 9 zeros, which is a billion. So there are 3 billion heartbeats per lifetime. This is a rough estimate. There may be 2 billion or 3.5, depending on the lifetime and the health of the person, how many heartbeats they have. But there are roughly a few billion heartbeats in the average person's lifetime if they live out their life expectancy. Interestingly enough, although there's a few billion heartbeats in the full lifetime of a person, there are also a few billion heartbeats in the lifetime of a dog and a cat and an elephant and many other and most creatures. Even birds, whose lifetimes are very short, and creatures whose lifetimes are very long, all have about a few billion heartbeats in a lifetime. Dogs and cats that live short lifetimes, how can they possibly have as many heartbeats as we have in our much longer lifetimes? Well, their heart beats much faster. And so by the time they expire, they still have had about 1 billion heartbeats in their shorter 10-year lifespan, and compared to our billion or so heartbeats spread out over a 100-year lifespan. And again, we find this to be true across many creatures. Don't know what this says, and it's not quite understood yet as why this is the case. But when we think about it, the numbers could have been anything. Some creatures could have had 1 million heartbeats in a lifetime, or 1,000, or maybe trillions. But they all turn out to have about the same number of heartbeats in a lifetime. Why? We don't know yet. Okay, this concludes exploring our mathematical toolbox that we'll use for the first unit of this semester.